Okay, good day. This is Dual Enrollment Pre-Calculus. I am Mr. McCulley, and this is the presentation for lesson number 36, Sequence Series, an arithmetic sequence and series. Let's get right to it. So today we got a lot of stuff. We're going to be talking about sequences and series, and specifically arithmetic sequences and series. Excuse me. The good news is that this is one of the easier sections that we will have talked about in this entire term. So lots of stuff we're going to talk about, what it is for something to be a sequence and how to define that both explicitly and recursively. We're going to write an equation for the apparent nth sum of a sequence, and that's a sequence in itself. And understanding the meaning of n with a exclamation point, that means n factorial, and we will discuss that. And then the section 8.2 goals, we're going to determine if a sequence is specifically arithmetic, and then we're going to use the explicit definition of an arithmetic sequence to find the terms in the sequence, and also use the common difference to find the explicit equation for an arithmetic sequence and its sum. So, what is a sequence? A sequence in math terms is a set of numbers that are related in some way. Each number is an element or a term, and they are usually listed as a sub 0, a sub 1, a sub 2, a sub 3, a sub 4, and so on. And sequences are defined explicitly, and sequences defined explicitly give an equation to find the nth term of that sequence. So what does that look like? Oh, let's move on to what it means to define something recursively. Sequences that are defined recursively have two parts. The first part is that they give you the first term or the first couple of terms, and then they provide an equation that finds the next term based on a previous term or previous terms. And so here's an example of a sequence that has been defined recursively. And so if I were to say, find the first five terms in the sequence, defined recursively, well, the good news is they already give us the first one. A sub 1 is the first term, and it's 4. And so the second term would be a sub 2. Now, in this particular instance, a sub 2 is the n value. And so what that means is that a sub 2 minus 1 times 4 would be the same as a sub 1 times 4. Now, we know from the first given definition that a sub 1 is 4. So that would be 4 times 4. And we know that 4 times 4 is 16. So our second term is 16. And if we wanted to find the third term, a sub 3, that would be a sub, well, if n is 3, then n minus 1 would be 2 times 4. And we just calculated that a sub 2 was 16. So 16 times 4 is 64. So the next term there would be 64. And then a sub 4, well, a sub 4 is going to be a sub n minus 1. 4 minus 1 would be a sub 3 times 4. 64 times 4 is 256, I'm pretty sure. And then a sub 5, the fifth and final term, would be a sub 4 times 4, equaling to 256 times 4. And I'm pretty sure that 256 times 4 is going to be 1024. Yeah, I'm pretty happy with that. And I screwed that part up, so 1024 ... There's our sequence. Next, Fibonacci sequence is a recursive sequence that cannot be expressed explicitly, meaning that it cannot have an equation that defines just that set of numbers. Now, we can definitely define this equation explicitly. Don't want to do that just now, but if you need me to do it, I can do it in class. But we can't define the Fibonacci sequence explicitly. So, but it's fairly simple. If I look at the recursive definition, they give us actually the first two terms. They say a sub 1, a sub 2 are both 1, and then the next term is the sum of the previous two terms. And so I can do that. If I set that up like this, the first term was 1, the second term was 1, the third term will be the two before it added together. Okay, so 1 plus 1 is 2. The fourth term will be the two previous, so 1 plus 2 is 3. The next term, 3 plus 2 is 5. 5 plus 3 is 8. 8 plus 5 is 13. So forth and so on. Now I have a little TED talk about the magic of Fibonacci numbers. They really happen quite a bit in nature, and they're kind of cool. So if you want, you can take a look at that TED talk and take a break from math. But we need to keep moving on. So factorials and factorial. That's how you read this. To find a factorial, you multiply n by each integer that is less than n and is greater than 0. So if I were to ask you to do 5 factorial, the way that you would write that is 5 times 4 times 3 times 2 times 1. And so all of the integers that are less than whatever n was, but greater than 0. So those are the 5 integers that are these are the 4 integers that are less than that number, and we're going to multiply it by. But that's the last integer greater than 0 is 1. And so this ends up being 120. Now you can do this in your graphing calculator. So if I clear all this stuff out and I say to my graphing calculator, I want to do factorial, I'm going to hit the math button. And I'm going to go over to probability right here, because factorial weighs heavy onto probability, and we can see right here that the fourth one is our little factorial exponent now, or factorial exclamation point. Now if we want to do that correctly, what we want to do is, if I want to find 5 factorial, I'm going to hit 5. Then I'm going to hit that math. I'm going to go over to probability, hit 4 to bring the factorial in, and there we see 120. Please note that 0 factorial is a special case definition. 0 factorial is 1, and it's kind of important that it works that way, because if it doesn't, a lot of things that we're going to talk about in probability here later on kind of falls apart. So it's a special case. Summation notation. The sum of the first n terms of a sequence can be represented by this sum symbol. And the sum symbol is just saying that we are going to add up all of the terms, and they say this little I here, this I is the index of summation, where 1 in this particular case, and it doesn't have to start with 1, it just usually does. Sometimes it starts with 0, sometimes it starts with 100, it just depends, is the lower limit of the summation, and n is the upper limit of the summation. And so basically it says plug every number from 1 to n, whatever it is, into this expression, and then add all of those values up. Now, just as a real quick example right here, and I don't know if I have examples coming up, but let's say I said what is the sum of n, let's do I equals, let's say 1 to 4, we'll keep it simple, of x squared. Well, what will that look like? It says plug all the values from 1 to 4 into x squared and add them up. Well, when I plug 1 in, I get 1 squared. When I plug in 2 squared, I get 2 squared. When I plug in 3, I got 3 squared, and then I plug in 4, I got squared. Now I know I stopped because I plugged in all the values from 1 to 4 into that function. So this is 1 plus 4 plus 9 plus 16, and let's see here, 9 and 16 is 25, plus 5 more is, no. Yeah, 9 and 16 is 25, plus 4 more is going to be 29, plus 1 is 30. So that is that particular sum. Properties of summation. If you have to sum up just a bunch of constants, then you just multiply the constant times the uh, upper limit of summation, provided that you start at 1. If you are multiplying an equation times a constant, you can factor out the constant and then just sum up the equation. If you are taking the sum of two separate equations, you can sum the first equation and add that to the sum of the second equation. The difference also holds true. So if you have the summation of a difference in two equations, you can do the sum of the first equation, do the sum of the second equation, and then subtract them. Definition: consider the sequence a sub 1, a sub 2, a sub 3, a sub 4. The sum of the first n terms of the sequence is called a finite series, or the nth partial sum, and it's denoted by that summation notation. And the sum of all the terms of an infinite series is called of an infinite sequence is called an infinite series, which would be denoted by this, where the upper limit is the infinity symbol. And if you have trouble drawing infinity like this, and even with my bad handwriting, it's not real good, two circles next to each other will also work. That's not very good, but there we go. A arithmetic sequence is a specific type of sequence that each term has a common difference. Now, if we go back to the Fibonacci sequence here, this is a sequence and it's defined recursively. But if I go, what is the difference between 13 and 8? Well, the difference is 5. The difference between 8 and 5 is 3. The difference between 5 and 3 is 2. The difference between 3 and 2 is 1. So the difference between each term in the sequence changes. In a arithmetic sequence, that difference does not change. So I have a arithmetic sequence here, and the difference between 9 and 7 is 2. The difference between 7 and 5 is 2. The difference between 5 and 3 is 2. And the difference between 3 and 1 is 2. We call that a common difference. Has the same difference, and that is the key point of an arithmetic sequence. All right, you have to have that same difference each time. Now we can come up with a general equation for a arithmetic sequence. In this particular instance, it's going to be a sub n is equal to d, the common difference, times n minus 1 plus a sub 1. So if we take this as our example, this first example of a arithmetic sequence, what we can do is we can say the common difference is 2, so we'll plug that in there. The first term was 1, so we'll plug it in there. And then this example is an explicit form of the arithmetic sequence. Now, we can use that to calculate any term. So let's say I wanted to find, I said find the fourth term, right? So that would be a sub 4. Well, all I have to do, let's draw 4 better. 2 times 4 minus 1 is 7. I come up here, 1, 2, 3, 4, there's the fourth term. And so now we can use this explicit form to find any term that we wanted to do. So if I said find a sub 50, all I would have to go is 2 times 50 minus 1. Well, 50 times 2 is 100, minus 1 is 99. So the 50th term in this sequence would be 99. And so what's good about defining functions explicitly is we can find any sequence or any term in the sequence, any place. All I need to know is which term I'm asked to find. Next, partial sum. The sum of the part of the terms in a sequence. So if I wanted to find the fifth partial sum, the sum of the first 5 terms in a sequence, that's how we would name it. Now, if I want to find the sum of an arithmetic series, this is the equation that I'm going to use. And I think I have an example. No, I don't. So let's do an example of that. Let's say I wanted to find the sum Well, let's just make one up here. So let's say my arithmetic sequence is 2. No, let's not make it 3. Let's go make 2, 5, 8, 11, 14, 17, dot, dot, dot. And I said I want to find the 20th partial sum. All right, so I'm trying to find S sub 20. All right, well, let's look at the variables here. N, that's the N, so a 20 goes there. A sub 1, that's the first term, so we can put a 2 there, that's good. A sub N, then we need to find the 20th term. Now I could go through and I can number those. That's going to take me some time. I don't like doing that, so let's find the explicit form. And remember from the previous page, a sub n equals the common difference times n minus 1 plus the first term. And so our explicit form, a sub n, will be equal to, well, what's the common difference here? The difference between 11 and 8 is 3. The difference between 8 and 5 is 3. The difference between 5 and 2 is 3. So my common difference is 3. N minus 1, and then my first term would be 2. So there's my equation. If I want to find the 20th term, a sub 20, I'm going to go 3 times 19, because 20 minus 1 will be 19, plus 2. And so let's see here. 3 times 20 would be 60, minus 3 would be 60, or 57, plus 2 would be 59. So the 20th term in this sequence is going to be 59. So this is a sub 20 is 59. And then we can divide that by 2. And so let's see here. 20 goes, I can reduce here. 20 goes into 2, or 2 goes into 20 10 times. So I get 10 times 61, which is 610. So if I were to add up the first 20 terms of this particular sequence, I get 610. All right, calculator example. Give the first 5 terms of the following sequence using a graphing calculator. So here we have some multiple n's in here. This is definitely not an arithmetic sequence, but it is a sequence that we can find using the graphing calculator. So I pull up my graphing calculator here, go to my y equals, we clear out the noise from previous lessons. Well, y equals, we want a fraction, so alpha y equals, hit 1 to bring up the fraction. We go back and check it out. So I got 1 plus parentheses negative 1 to the n on the top. And so 1 plus parenthesis negative 1 raised to the x on the top. And then it was just 2x on the bottom. Come on. There we go. 2x. And so we want the calculator to do all the work for us. And you know what? Let's have it give us our answers as fractions. So if I go math and I hit 1 to get a fraction there, if I go second and I want to set up my table because I wanted to make sure we're doing it, we'll start with 1, go by ones because we want the first 5 terms. Hit enter to turn it to auto because we want the calculator to do all the work. Second, graph, here we go. Our first 5 terms are going to be 0, a half, 0, a quarter, 0. And so how many terms do they want? First 5 terms. 0, 1 half, 0, 1 quarter, 0, dot, dot, dot. There it is, our sequence. Next, it says given the recursive definition, find the first 5 terms of the sequence. So this one's labeled a little bit differently than the one I did before. And so we'll start, they tell us the first term is 2, so we'll leave it there. And so this one I had a sub n and then a sub n minus 1. Well, we want to find the second term, a sub 2. Well, a sub 2 is in the k plus 1 term. So if k plus 1 is 2, then k would just be 1. A sub 1 plus 3. Now a sub 1 we just defined to be 2. So we have 2 plus 3. It gives me 5. My next term is 5. If I want to find the third term, a sub 3, well, a sub 3 is in the k plus 1 value. So if k plus 1 is 3, then k is just 2. I want to add 3 to that. Now, we already found that a sub 2 is 5, so I'm going to put a 5 there, plus 3, that's going to give me 8. Now, you'll notice this is kind of the sequence that I just came up with, it looks like, because each time I'm going to add 3. So the next one would be 11, and then the one after that would be 14, I think. Pretty sure. Yeah, that seems right. Does that mean I made a mistake on this last one? Let's check. Nope, I did it right. Okay, we're good. I thought I was going to have to start over. Next example, expand the following summation notation and find the sum. We have already done that one. It says write the following series in summation notation. And so we want to come up with a summation like that. And so we'll use our little I and we'll start with 1. And I see 1, 2, 3, 4, 5 terms. So my upper limit is going to be 5. And my suggestion is whenever you have fractions and they want you to do a summation, and this is just kind of a general rule of thumb, make an equation for the top one and then make an equation for the bottom one. Well, this doesn't change. It's always 1, so I'm just going to put a 1 there. That looks like that's going to work. And then I have to find out the relationship 1, 4, 9, 16, 25. Well, hey, I know what those are. Those are all perfect squares. 1, 4, 9, 16, 25. And in fact, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. And notice I got to go from 1 to 5, so I want to have all those numbers. So we're just going to call it I squared. That's a 1, by the way. And so that is my summation notation. Next, write an example of an arithmetic sequence whose 10th term or whose 4th term is 10 and whose 6th term is 16. Write an explicit formula for the parent nth term of the sequence. Now, this one, it looks hard, but it ends up being fairly easy because if you notice, a sub n equals d times n minus 1 plus a sub 1. This is a linear equation. And so I can get past all of this stuff because I don't know what the common difference is. I don't know what the first term is, but I do know that the 4th term is 10 and that the 6th term is 16. So I'm just going to find the equation of this line. And so then you're going to find the slope, m, and you'll notice that the slope and the common difference end up being the same thing. So 16 minus 10 over 6 minus, let's see here, 6 minus 4, that gives me 6 over 2, which is 3. And then I can use the point slope form, and we'll go y minus y sub 1, so 10 equals m times x minus x sub 1, which is 4. So I get y minus 10 equals 3x minus 12, and then y equals 3x minus 2. Now that's the linear equation, and all I got to do is change it to this form and say, so we're going to change to explicit arithmetic sequence form, and we'll just say a sub n equals 3n minus 2. And that will work. And just as a check, if I want to find the 6th term, 6 times 3 is 18, minus 2 is 16. So I am happy with that expression. Okay, so our last example here, find the sum of the first 300 positive even integers. Well, we can do that. Let's see here. The sequence, or the series would be, oops, need the right tool here. Come on now. Crayon. There we go. I don't know why I did that. I don't know. Okay, there we go. So the series is going to be the first, that's going to be my first positive even integer. And then, let's see here, the next positive even integer would be 4 plus 6 plus dot 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 until we get to the 300th positive even integer. Well, we got to figure out what that is, okay? So if I go back to my general form of an arithmetic series or sequence, and clearly this is going to have, because it'd be 2, 4, 6, 8, 10, got a common difference. A sub n equals a common difference of 2 times n minus 1 plus the first term, which we found to be a sub 2. And so a sub n equals 2n minus 2 plus 2. A sub n equals just 2n because those 2's cancel out. So if we want to find the 300th term, we want to find a sub 300. So 2 times 300 is 600. So this last term here is 600. So now we have our first 300 positive even integers. And so we want to add those up. And I don't want to do it by hand, so we go back to that equation for finding the nth partial sum of an arithmetic series, and that would be s sub n equal to n times a sub 1 plus a sub n all over 2. In this particular instance, we're finding the sum of the first 300 terms, and since there are 300 terms, when the first term was 2, the last term we calculated to be 600, and that's all over 2. And so we'll just go ahead and we'll grab our calculator here, and it was 150 times 602 divided by 2. That means that 45,150 45,150 is the sum of the first 300 positive even integers. We'll put a box around that, call it a day, and say that the Star Wars fun fact of the day is Darth Maul has 10 horns on his head. Originally, they were meant to be feathers, but there is a rumor that the art department misinterpreted the concept art and turned them into horns. He looks far more menacing with horns than I think he would with feathers. What do I know? I'm just a math teacher. That's all I got today, folks. Have a good day. Bye.